Hello, in this video on optics we are going to discuss about the optical instruments. Now the optical instruments are the ones obviously which are used uh, in daily or daily basis, you can say, to some extent, or also in case of the laboratory experiments that we carry out. So we have the optical instruments uh, which obviously help us to view the objects which are to be observed in a better way. Now, a few of those optical instruments that I'm going to discuss in this video include the first one being uh, the magnifying glass or the reading glass, which is a simple microscope. So we are going to deal with microscopes and telescopes in this segment. So first up, we have the simple microscope, which is nothing but a magnifying glass, a simple convex lens. But we have already discussed about convex lenses, but in this case, the convex lens will have a particular form or particular use over here, and that we are going to observe with our derivation or with the formula that we are going to end up with. Now, in this case, if we have a convex lens and there's a principal axis passing through the optical center, and then we have an object. Now, suppose we consider the focal length to be this much that I have marked right now, and we consider an object placed within the focal length, a small object to be observed, usually the letters of your book that you study, the small letters behind any kind of package that you uh, wish to read by using the magnifying glass. So these are those small letters, and mind you, you have to read them. If you wish to read them, you take the magnifying glass really close to it, such that that object now lies within the focal length of the given lens. Now, what happens over there is that first up, we are going to construct two rays from the tip of that object. So there's the first ray which is going parallelly. And as you know that parallel light rays, when they are rendered onto the lens, they pass through the focus. So I'm going to take this through the focus on the other side. Luckily, that was a straight line. And then the other ray is going to pass through the optical center as we have been constructing them. So this is going to pass through the optical center undeviated. Now, as you can see that these two light rays are actually they are diverging in a sense, and they won't meet. So what happens is that we have already done this kind of a diagram, ray diagram, where the object within the focal length of the convex lens, uh, that the rays do not meet on the other side, and they have to be produced backward in order to meet. So I produce the first ray in the backward direction and the second ray as well. So this first ray, I'm taking it in the backward direction. I hope I managed to get it straight, almost. So this is more or less the ray taken in the backward sense. I think I've messed it up. I'm redoing it. So now it seems nice and clear. So we have this image formation, and probably this is the eye of the observer who is trying to observe the image. And as he will be observing this image, which is enlarged and a virtual one, because the rays are not actually meeting, they have been produced backward. Now, from all of this, what we get is that, let's say that the object is at a distance u, and you have the image to be formed at a distance v. So we know that the magnification in this case is simply going to be v over u. But here we define the magnifying power as something in a different way. So we define the magnifying power in this case as the ratio of the angle that is subtended by the image to that subtended by the object. Now, as you can see, both the object and the image, they are subtending the same angle at the lens. Now, the angle that I'm talking about in this case, I'm showing it to you that we have over here is they're actually these angles. This is the angle. As you can see, this angle is theta I, that is the angle subtended by the image. Now, if I am to consider the case of magnification, then I'll have to observe. Now, imagine you are observing a certain object which is placed in front of you, and another object which is exactly behind it. And when you are, suppose you have a mountain in front of you and a mountain behind it, and if the tip of both those mountains subtend a same angle to your eye, then you will hardly be able to observe the second mountain which is behind, or you won't be able to compare the sizes of the mountains. So it is just like the same case. So if you have an object whose image is exactly behind it and they are subtending the same angle, then there is no point in comparing them. So what we have to do is we have to consider the the object to be at the same place as that of the image. And if the object stays there, then that would subtend a different angle altogether. Now, that angle subtended is the angle subtended by the object theta O. So, theta O is the angle subtended by the object when it is considered at the place where the image is formed. Now, for a normal human eye can observe any object distinctly at the least distance of distinct vision, and that is equal to 25 centimeters for a normal human eye. You can distinctly view an object at this distance. If it is something less than that, then the distinction won't be correct or won't be precise. You won't be able to distinguish between, suppose you can say the lines on your hand. If you take them really close to your nose and you try to observe them, then they get mixed up. And if you are keeping them at a certain distance and observing your palm, then you can see the lines on your palm. So it is just like that, that you need to maintain at a certain distance away from your eye, and that distance for a normal human eye is 25 centimeters, and this is also known as the near point. Now, away from this point, right up to a greater distance, right up to any greater distance, you have the far point. A greater distance can be anything. It can be 100 meters, which for 25 centimeters, when you compare them, the 100 meters is obviously an infinite length for 25 centimeters. So the far point, you can say, extends right up to infinity. The far point extends right up to infinity. So we'll get back to the case of far point. But as of now, what we wish to consider is that we will be considering the image distance for clearly and distinctly viewing any object to be at the least distance of distinct vision. So as a result of that, what we get is that suppose we have the image, suppose we have the object over here as AB, and we have the image as A prime B prime. So we know the drill that we have been obtaining the cases of similar. We have been considering the case of similarity between the two triangles, and we also have obtained this case that A prime B prime over. Now in this case we'll be considering the CB dash O triangle. So A prime B prime over over B over CB prime. will be equal to the base distance. I beg your pardon, this is not the case. Well, theta I over theta O. This is I got distracted. Theta I over theta O. Now, these angles are really small because you're observing small objects. So, for smaller angles, as these angles are very small angles, you have these values to be nearly equal to tangent of those angles, tan theta I over tan theta O. Now, tan theta I over tan theta O gives me, if you observe those triangles A dash, B dash, and O, and another triangle as CB dash O, then what you have is the perpendicular over the base for tan theta I, and then the perpendicular over the base for tan theta O. Now the bases being same, they cancel out. What we are left with is A dash B dash over CB dash that I was trying to write a few moments back. And now CB dash, as you know, is actually equal to the length of the object that has been considered. So that is equal to AB. CB dash is equal to AB. Now, we already know from the similarity of the triangles A dash B dash O and ABO back when we were obtaining the thin lens formula. We know that this is going to be equal to B prime O over BO. Now, B prime O in this case is, as per the sign convention goes, it is negative of D, and BO is negative of U. So now you have the magnifying power to be equal to D over U. The problem is that when you go to a shop to buy a magnifying glass of a certain power, then you have a fixed value. Now the object distance over here can change because you can place the object anywhere, any point within that focal length. So you need to have fixed values in order to obtain a definite magnifying power. So what we do is we have the thin lens formula with us. So we have 1 over V minus 1 over U to be equal to 1 over F. Now 1 over V, in this case, using the sign conventions, you have 1 over minus D. And similarly, the object distance is always negative, as I said, because it's considered to the left of the lens, and the focal length for a convex lens is positive, so it is 1 over F. Now, this becomes plus 1 over U, and the minus 1 over D can go on to the other side and get added to the reciprocal of focal length. So we have 1 over U to be equal to 1 over F plus 1 over D, and we just substitute that value over here. So the magnifying power in this case becomes D times of 1 over U, which means D times of 1 over U, as we have obtained, is 1 over the focal length plus 1 over the least distance of distinct vision, which is a fixed value for the normal human eye. As I said, it is 25 centimeters. So what we end up with is that we have the D can get into that bracket and get multiplied. So we have now a value of magnifying power as D over D is 1 and D over F remains as such. So we have now a magnifying power which can be determined by knowing the focal length of the given lens. We can know the focal length of the given lens from the lens maker's formula, provided we know the radii of curvature of both the sides. We need not be concerned about that. The shopkeeper who provides us with the magnifying glass has got the printed package, and they print it on the basis of what they have made, and they would have made a proper focal length, a lens with a proper focal length by considering the curvature of both the surfaces by following the lens maker's formula. And they know very well the normal human eye is 25 centimeters with least distance of distinct vision. Then the magnifying power can thus be determined, and they would have printed that on the package of the magnifying glass. So you just have to buy it. So now this is a fixed value. Consider the case where you wish to obtain, where you wish to see an object to the farthest point that you can. And in that case, you need to have the image at infinity. Now, this image can extend up to infinity and you can view them distinctly. Now, for the image to be formed at infinity, you need to have the object at the focal length. So we call that as the normal adjustment. Let me adjust that over here. So normal adjustment. Now, in case of normal adjustment, what we do is we place the object right at the focal length of the given lens, as a result of which the image distance now goes to infinity. Now with the image distance going to infinity, you have 1 over f to be 1 over u to be is equal to 1 over f. So you put that in this formula for magnifying power. So you have the magnifying power now in case of the normal adjustment for the image obtained at infinity, which is the far point as you know it. So in that case, you have the magnifying power to be equal to simply d over u. Instead of u, you have the value f because u is equal to f. So if you place the object at the focus of the given lens, then you get a magnified image which is received at the far point, and you can view it properly. So this is how the magnification in case of a simple microscope goes. The magnifying power, we'll be discussing about the compound microscope as well as the astronomical telescope in the upcoming videos. Till then, thank you for watching.